So it is my pleasure to introduce Junliang Shen, who's going to give us the first of two talks on the moduli of Higgs bundles and the conjecture.
Okay, can everyone hear me? Okay, so I'm pretending as if I'm Davesh Maulik. I cannot mimic his English, but I'll try my best to do the math part. Okay, so the theme of the talk will be about model of Higgs bundles, and in particular with a focus on the P equals W conjecture. So the goal is to discuss the modular space of Higgs bundles on a curve on Riemann surface, and some of the recent activity studying its cohomology. So as Sheldon announced that there actually will be a change of the plans. This was Davesh's original plan. So today's plan will be the same. We'll be doing an introduction to Higgs bundles, and I mean the modular spaces and its cohomology. And then there will be only a second talk which will involve more details. So today is the introductory part. Okay, let's start with the warm-up, which is a story happened many years ago concerning stable vector bundles. And this is actually in some sense the first exciting story connecting algebraic stability, topology, and metrics. So first, let's recall some facts about the stable vector bundles. So let's see be a smooth projective curve over the convex numbers. In other words, it's a Riemann surface. Let's assume it has genus G. And given a vector bundle, holomorphic or algebraic vector bundle E on the curve of degree D and the rank R, we can talk about its slope, which is basically the rational number given by the degree of this vector bundle over the rank of it. So using this, we can talk about the notion of stability and semi-stability. So in particular, we say that a vector bundle E is stable if for any strict subvector bundle F, the slope of F is strictly smaller than the slope of E. So because everything is about degree and the rank, so it's fairly easy to check whether a vector bundle is stable or not. So now we consider the modular space, which we denote by N. Rd here, the S means the stability. So consider the modular space of stable vector bundles of degree D and rank R. So if we impose some numerical condition, namely that the rank is co-prime to the degree, so then there will be no strict semi-stable locus. So in particular, the stable locus will be exactly, so in general, it's quasi-projective variety, but if you impose the co-prime condition that rank is co-prime to the degree, then it is projective. So it's a smooth projective variety whose dimension is linearly dependent on the genus G and quadratically dependent on the rank. So in particular, when you increase the rank, then the dimension of the modular space increases fast. So you see from the dimension formula, which is R squared times G minus 1 plus 1, this formula, it has nothing to do with D. So it does not depend on which degree you take. Okay, so now let's recall the Narasimhan-Seshadri theorem, which is the beginning of many exciting stories concerning vector bundles and their generalizations, namely Higgs bundles. So this is a connection between two different worlds. And on one side, it's the topological data, namely on the left-hand side. So I hope people can see my mouth. Yeah. So the left-hand side concerns irreducible unitary representations of the fundamental group of the curve of the Riemann surface. So yeah, so the pi 1 of the Riemann surface actually is from our first topology course. We know what it is like. So it consists of 2G loops, AI and BI, satisfying that the product of the commutator of them is equal to the identity. So that's the only relation satisfied by these generators. So then for every irreducible unitary representation of the fundamental group, the surface group of rank R, there is natural correspondence to stable vector bundles on the Riemann surface of rank R of degree 0. So in other words, there's the left-hand side is complete topological. It only considers the pi1 representation. But every time you're given one, you get an algebraic datum, which is a stable vector bundle of degree 0. So to see, what's the meaning of the things on the left-hand side? Well, you have this equation. So what you do is you insert the unitary groups into this AI and BI. So the left-hand side is parameterized by matrices AI and BI. Just replace this AI, BI, the generators by unitary matrices satisfying this equation. And so here's some idea of one of the proofs. So for every unitary representation of dimension R, we can, by the Riemann-Hilbert correspondence, we can turn this into something slightly more algebraic, which is a flat connection, a unitary flat connection on a bundle. And there is a highly non-trivial step, which you can turn this into a holomorphic vector bundle. So we turn something from topological, to algebraic, and there will be a clearer and a more generalized picture of this, as we will see in a minute. Okay, but here we consider the case of rank R degree 0, and as I mentioned in the first slide, so to get a smooth projective varieties, we're more interested in the cases where the rank is co-prime to the degree. So this is particularly not the case, but there actually is a version, the twisted version, which fixes this problem. So if we consider a non-zero degree D, then we can also make this work. So we can, instead of considering the pi1 representation directly, we puncture the Riemann surface, and we consider irreducible representations of this puncture Riemann surface where we fix the monotomy at this point. So the monotomy of this point is given by a root of R's root of unity, where this D, here the e to the power of 2 pi I over R, of 2 pi I D over R. So this D exactly is the degree. So in other words, so there is the natural diffeomorphism from the algebraic modular space, which is the modular space of stable vector bundles of rank R degree D, to the data of the left-hand side. So as I said, it's nothing fancy here. So you just consider it's a parameter space of 2G matrices AI and also this BI satisfying this commutation relation. And of course, to consider modular space, we have to consider equivalence classes. Namely, we modulo out the conjugate. So the UN acts on these matrices by conjugation, and we just quotient this out. Okay, so the right-hand side is an algebraic variety of dimension I just explained, and the left-hand side is not algebraic, but actually it's very close to be algebraic. The only non-algebraic part here is the unitary group, UR. So this is not an algebraic group. So the Siemens-Chaudhary theorem relates topological, which is the left-hand side concerning pi1, and algebraic data associated to the Riemann surface C. And actually, we will see immediately that there are interesting applications. So actually in the history of the development of this subject, these two worlds are interacting regularly. For example, in the early stage, people use the Morse theory on the left-hand side, namely by analyzing these matrices to calculate topological invariance associated with the modular space of vector bundles. So the question, what if we want to make the left-hand side slightly more algebraic? Namely, this is fairly easy to do. So the only thing we do is we replace this UR, which is the only non-algebraic data in the left-hand side, by GLR. And R by this is the group, the algebraic group of R by R invertible matrices, and we keep all the equations the same. So the same, the pi1 representation. So in other words, so we can just instead of considering these matrices with the commutation relation, we consider unitary matrices. We consider the general linear matrices in the general linear group. And what's the corresponding thing at the right-hand side? So at a first glance, it seems to be very hard to further extend it because we already consider stable vector bundles. So the answer, there's actually an interesting answer from the abelian Hodge theory, which actually is an upgrade of Narasimhan-Seshadri's story to the second row here, replacing UR by GLR. So the 3 question mark on the right-hand side here will be given by the stable Higgs bundles. So instead of only considering vector bundles, in some sense, the more natural data we should consider is the pairs, which we will introduce in this slide. So a Higgs bundle is a pair E, which is the bundle part, and also phi on the curve. So of course we can, I think the vector bundle case, we can talk about the rank and the degree. So this data consists of a algebraic or holomorphic vector bundle E of rank R and a degree D, and the Higgs field, which is basically an anamorphism of the vector bundle, but you twist it globally by the canonical bundle or the cotangent bundle of the Riemann surface you start with. Then the notion of stability is similar. So we say that a Higgs bundle E phi is stable if for any strict sub-Higgs bundle F, so meaning that F is a sub-bundle of E which preserved by phi the Higgs field. So we require that the slope of F is strictly smaller than the slope of E. So we just move everything to instead of just one bundle, but a pair, a bundle with a twisted anamorphism. So now we consider modular space. So we use MH. So here the H means the Higgs. RD to denote the modular space of stable Higgs bundle on the Riemann surface. And since you have the extra data of the Higgs field, you can imagine that the dimension actually is larger. So because there's some freedom for the choice of the Higgs field, so the dimension is twice as the dimension of the modular space of stable vector bundles. And here, one of the key features of comparing to the unitary story is that no matter how you choose R and D, so even you choose them to be co-prime, the modular space won't be projective. It won't be compact. So no matter how you choose it, it will be quasi-projective. So one of the easiest way to see it is to consider the scaling action, the C star action on the Higgs field. So not much thing you can do for the bundle part, but you can scale the Higgs field by scaling. And you take the lambda times this phi and you make the lambda go to infinity, then you convince yourself that the limit is not there. So in particular, no matter how you choose the rank and degree, the modular space is always a quasi-projective variety. Okay, so here, let's give a more geometrical, intuitive way of thinking about Higgs field. So what's the Higgs field actually? So the Higgs field is an element in home from E to E tensor the canonical bundle. And so it's actually from their duality in our algebra geometry course, the undergraduate algebra geometry course, you see there's a way to actually to take out KC, the canonical bundle, by considering the dual. So the dual side will exactly be the extension 1 of E. Okay, so but what this is? So this is, if you consider vector bundles, this extension 1, the dual of the extension 1 is nothing but a cotangent vector, the space of cotangent vectors to this element E. So in other words, so you can easily construct an open subset, which you basically take, you just take the locus of rank R degree D stable vector bundle, and you take the total the total space of the cotangent bundle of it. And so this is actually, this more or less will be the MHRD, because it consists of the data of the vector bundle together with a Higgs field. But actually, because the stability conditions on both sides are different, for any stable vector bundle with some Higgs field, it will be giving you a point in the model of stable Higgs bundle. But for any stable Higgs bundle, if you forget about the Higgs field, it may not be a stable vector bundle. Because for Higgs bundle side, you're not only testing the sub-vector bundles, but you are testing a limited subset of it, which is the sub-bundles preserved by the Higgs field. So you see that this is actually a Zariski open dense subset of MHRD. Okay, so So on the total cotangent bundle of the NS, the model of vector bundle, there is a natural holomorphic or even algebraic symplectic form. And so it's a very nice structure that this algebraic symplectic form actually can be extended to the entire modular space of Higgs bundles to do this partial compactification, which makes the latter actually as a hyperkähler manifold. This is a highly non-trivial result. So because for an open variety, being holomorphic symplectic is not exactly the same as being hyperkähler, but in this case it is. It is indeed hyperkähler. Okay, so this is the first definition for the model of Higgs bundle. We consider bundles with a Higgs field, but there's actually, if you like better the modular space of stable objects or stable sheaves on higher dimensional varieties, actually there's another description using surfaces. So now let's take X to be, instead of just a curve, the total space of the cotangent bundle of curves. So this is actually a Calabi-Yau-2 surface. So this, by the way, this Calabi-Yau-2 point of view actually is very important for this story in some sense, and makes many rich connections to other areas like representation theories and enumerative geometry, Donaldson-Thomas theory. So probably some of these ideas will be mentioned later. So okay, so let's consider T star C, and for every given Higgs bundle, which is E together with phi, which is the Higgs field, we can turn this into a coherent sheaf on the surface. So this correspondence nowadays is referred to as the BNR correspondence, the Bourvil, Simon Ramanan. So this is the cartoon actually drew by Davesh. So you have this is the total space of the T star C, and to visualize Higgs bundles, you just consider, so this is the the cotangent direction. So this is a surface T star C, and see these red curves are the support of the sheaves given by Higgs bundles. So if you could turn a Higgs bundle into a coherent sheaf on T star C, and the support of these objects will be degree R is the rank, degree R cover over the original Riemann surface, original curve. So point-wise, actually, this is linear algebra. What do you do? So for any point on the Riemann surface, the R points, which are the pre-images given by just the eigenvalues of this n by n matrices restricting over that point. So you have an endomorphism of this vector bundle twisted by Kc, but after restricting a point, it's just n by R by R matrix. And then you consider the eigenvalues of it, which are just these points actually. Okay, so then the modular space, there are two ways to think about it. One way is that modular of Higgs bundles, which is the partial compactification of the total cotangent bundle of the model of vector bundles. Another way is just modular space of one-dimensional sheaves on the surface X, on the local Calabi-Yau surface X. So, okay, so comparing to the vector bundle case, actually this modular of Higgs bundle admits another structure called the hitching map or hitching fibration. In the last 2 decades, actually, the notion of hitching fibration is much influencing other areas. So let's just introduce it. So, the structure of the hitching fibration will be a proper Lagrangian fibration. So as I mentioned earlier, this modular space is a hyperkähler manifold, is a holomorphic symplectic variety, and this admits a Lagrangian fibration whose base is affine. So this is the affine space whose dimension is half of the dimension, of course, of the total space. So the quickest way for thinking about hitching map is just the affinization map. So the hitching modular space, as I mentioned, is not proper. But you can consider the affinization map from the modular space to the spec of the global algebraic sections, the algebraic functions on it. And then this is exactly the hitching fibration. So in other words, this is the modular space is not proper, but it's almost proper. So up to the affinization map, it's proper. So this is the first definition. but still it seems to be pretty abstract. So let's give another way using one-dimensional shifts on surfaces to describe you actually how to visualize the vibration of this Hitching vibration. So given any point in the Hitching base, AD, so this, by the way, the AD, so that's the AD, the Hitching base can be viewed as the space of the space of actually the effective divisors in X proper over C of degree R. So this is a collection of spectral curves, the curves I drew in, well, Davesh drew in red, the degree R map over the base curve, and you just collect all of them, and this forms an affine space. It's a linear system in open surface. So then for any point you get this curve, you recover this curve, which I call this CB, whose genus is exactly the dimension of the base, which is D. And then for any general member of the base, so the corresponding curve is smooth, and the Hitching fiber is nothing but just the Jacobian variety attached to this curve. So it parameterizes the line bundles of fixed degree on that curve CB. So if you want to switch it back to the original language of Higgs bundles, so these Higgs bundles are given by these one-dimensional sheaves, which are the I lower star of this line bundle. So you have a T star C, you have T star C, and you have these curves CB, and you just consider line bundles supported on this CB. And this is a proper variety, of course, which is a abelian variety, and this is actually the entire Hitching fiber for this general B. This is a cartoon for the entire Hitching vibration. The general fiber, well, these are the tori, abelian varieties for various curves. But when, because this AD is the full linear system, so if you can make the curve degenerate, and then it's more and more singular. So in particular, if you degenerate a little further to integral curves, then the fiber is still a very well understood, well, it's complicated, but relatively well understood object, which is called compact by Jacobian. So it parameterizes instead of line bundles, it parameterizes rank 1 torsion-free sheaves on that curve. For example, the first example is the case of nodal curve, where you can involve these objects which are like ideal sheaf of the node. So these are not line bundles, but these are objects in the compact by Jacobian. But actually, if you go further, you go to deeper strata, and you get more complicated stuff. For example, as I mentioned earlier, so the total space, the NRD, you consider just the space of all vector bundles where you impose the trivial Higgs field. You consider a stable vector bundle of rank R degree D, and the trivial Higgs field. And this gives a point in this modular space, and the entire modular space NRD actually lies over the preimage of 0 of the base. But actually, this is not only irreducible component. There are other irreducible components given by nilpotent matrices. So this is the case of matrix 0, but there are also nilpotent matrices. So the characteristic polynomial is 0, but the Higgs field is non-trivial. Okay, so yeah, this is the takeaway for this picture. So a Hitching vibration actually is an abelian vibration, in the sense that it's a degenerating. You have a flat morphism to the base, where a general fiber is a torus, as a abelian variety, and special fibers are complicated. Okay, now let's come back to our original motivation in the introduction, which concerns a generalization of the Harder-Narasimhan shadowy theorem. So this was developed in the 80s, from the 80s to 90s. Actually, I didn't check in the previous AMS Summer Institute, for example, 40 years ago, whether these topics were discussed. Oh, actually, it is. So it was discussed in Santa Cruz by Simpson in 95. He gave lectures, and before that, I didn't check. Yeah. So, okay, so this is the two sides of the story. The one side, as I said, you just replace the unitary groups by GLR. So this is the equation the left-hand side is the topological side we discussed earlier. And the right-hand side, which is the thing we just introduced, we consider stable Higgs bundles. Okay, so these are, now the good thing is that now these are two different algebraic varieties, because we as I said, the only non-algebraic gadget is the UR, which is replaced by GLR. So these are now is a picture of two algebraic varieties which are diffeomorphic. So this diffeomorphism extends the diffeomorphism given by Siemens-Chaudhary, and it's a highly non-trivial result due to a lot of people in its developments. I just mentioned a few names. We'll call it Donaldson, Hitchin, Simpson, and yeah. So now these two are algebraic varieties, and so inside which there are some interesting natural locus. So in the Higgs modular space side, as I mentioned, there is actually the entire modular space of vector bundles, which lies over the preimage of the zero of the Hitchin vibration. So it's one of the component there. But you can ask what this is turning to the left-hand side. Well, this is given by Siemens-Chaudhary, which are unitary representations. So yeah, so in particular, the locus in the right-hand side is algebraic. It's an algebraic subvariety. And moreover, it is actually a Lagrangian in that hyperkähler manifold, holomorphic Lagrangian. And the left-hand side is not even algebraic. So it's a unitary representation. This is a real manifold inside this complex algebraic, right? Okay, so now you have two spaces which share the same topology and they have very different flavors. So these are the two sides of this Abelian-Hodge theory. And actually, well, from now on, as I mentioned, if you impose the condition that RD is co-prime, then you can rule out the possibility of having strict semi-stable points. So in particular, so now both sides are, yeah, so you don't have to consider semi-stable points or polystable points. So both sides themselves are already smooth quadratic projective varieties which behave well. And yeah, this is the equation I just, well, it's just written down for the character variety. You have matrices AI, BI satisfying this commutation relation. So the commutators of AI, BI, and you take the product of them, it's almost the identity up to an primitive R root of unity. So here, this D, this R, so you see that for this equation, the only dependence on the rank and the degree, well, the rank depends on is the size of this matrices, but the only place where the degree comes into picture is the choice of the primitive root of unity of R. Yeah, let's give some examples of this geometry. So the first case, we consider what happens when R is equal to 1. So D can be chosen anything. For example, we can, because I want to choose D to be co-prime to R. So if R is equal to 1, then D can be anything. So the group we consider is GL1. So GL1 over the complex number is C star or GM. So then you realize immediately that the second equation, the AI, BI, the commutation relation, this is the empty condition because GL1 is a commutative group. And so in other words, for the character variety of rank 1 degree 0, you're doing nothing but choosing 2G matrices. And that's it. So in particular, this variety as an algebraic variety is C star to the power of 2G. So this is a very simple variety, it's toric, actually. Okay, let's turn to the other side. The Hitchin modulus space, the model of Higgs bundles of rank 1 degree 0. So let's recall what it is. So it involves the choice of a line bundle, a rank 1 vector bundle, which is line bundle. So the choice is given by the Jacobian variety of the original curve you start with, but also a Higgs field. But in this case, the Higgs field is just the choice of a differential form, a holomorphic differential form. So in other words, you see that the Higgs bundle modular space is the Jacobian variety of the curve times CG. Yes. From this, you already see that, okay, so it requires some work to convince yourself that these two algebraic varieties are actually diffeomorphic. So the easiest way to see it is because for C star or GM, the topological type of it can be written as S1 cross R1. And then you just consider product of these guys and you regroup them. You regroup the S1 factors, you get an abelian variety. And you regroup this R, this affine part, and you get actually the CG, which you can view this as a space of holomorphic differentials. So, but it's quite obvious that this diffeomorphic, I mean, these two sides of the, the algebraic structures of these two varieties are quite different, because the left-hand side only depends on G, but right-hand side depends on the complex structure of the Riemann surface you start with. Okay, let's do a slightly more non-trivial example, which is in some sense, the only non-trivial example I will do. So now let's go to the rank 2 case, but let's assume that the curve, the underlying curve is an orbifold curve. So if you don't like orbifold, actually everything can be turned into the language of using parabolic structure. But let's take the C to be, you take an elliptic curve, which is a natural involution by +1, -1. So you send a point to the minus of this point, and you take the quotient. So this is a orbifold P1. It's a P1 with 4 orbifold points. And in this case, if there is no, the modular space of the Higgs modular space is nothing but you first take the rank 1 modular space over the elliptic curve. As I explained earlier, this is nothing but E cross A1. This actually works for any curve, but which you replace E by the Jacobian. But then you quotient out by this involution, but plus -1, which will create 4 singularities, which are given exactly by the 4 orbifold points of this curve. And you take the quadrant resolution of it. So the MH is the quadrant resolution of this quotient, that E cross A1 modulo this Z2. This is the picture, actually. This is the picture. So a general fiber is nothing but just elliptic curve. E itself is isotrivial fibration, but a central fiber contains a thickened P1 as a fat P1 together with 4 exceptional divisors. So yeah. Okay, in this case, one can also analyze what's the character variety. This is actually done by decades ago. So the character, because now you don't have the genus parameter. This is an orbifold P1. So all the data only focuses on these 4 punctures. So it's basically, so the character variety is nothing but you consider 4 matrices whose product is identity, and it satisfies some conditions. So it's a complete elementary object, and with some work, one can show that the corresponding character variety for this geometry is an affine cubic surface. So you take the cubic surface in P3 and then you remove a triangle from it. Okay, so yeah, this example will come back in a few minutes. So, well, in general, we know that this modular space, the Hitching modular space, is far from being affine because it contains, even in the rank 1 case, it contains a lot of abelian varieties. But character variety is always affine by the definition. So in particular, this suggests that this morphism, this map from the non-abelian Hodge correspondence, this blue star is highly transcendental. It's very far from being algebraic. So actually, this even changes the complex structure. So it's not even complex and elliptic. So yeah, the takeaway for this is that these two are very different algebraic varieties. Okay, but nevertheless, they share the same underlying topological spaces. So one can study their, for example, cohomologies and topological invariance. And actually, it doesn't matter which side you look at. You can, because it's the same, it's the same manifold. So you can either look at a singular cohomology with Q coefficients. Well, here the cohomology means the singular cohomology with Q coefficients. You can either look at it in algebraic side, namely the model of Higgs models, or the topological side, the pi1 representation space. So before discussing this, maybe let me first mention that actually from 80s to the 90s, there are a lot of activities concerning the study of this NRD, which is the model of vector bundles, and this is fairly well understood. But for MHRD, the model of Higgs bundles, so the cohomological study, I think, started from Hitching in the 80s for the rank 2 cases, but even till this moment, and there's still a lot of open questions, and hopefully, well, much progress will be made by the 2035 conference. Okay, let me first describe something we know. So, okay, so for this modular space of vector bundle, one of the very first results is that we know that the cohomology is generated by tautological classes, which are the natural classes defined by universal bundle. So in a modular vector bundle case, this was actually first proven in a famous paper of Attila Bott on Yang-Mills equations over Riemann surfaces in the 80s. But the same result actually holds for the modular space of Higgs bundles, stable Higgs bundles. So we consider this is since this is a fine modular space, there is a universal family, which we denote by E univ. And then we can just take the Chen. So this universal bundle lives over the product of the modular space cross the C. It's on the product. And then you take the Chen class, which will give you classes on the product, and then you just take the Kunis components. In other words, you do the most natural thing you can do. You start with the vector bundle. The most natural class you can take is to consider Chen classes, and then you consider the Kunis components of it. And by Jan Markman, who proved this, I think in the beginning of the 21st century, that this CKR, this generalizes Attila Bott theorem that the CK gamma, so here K means which Chen character you take for the universal family, and the gamma means which class you integrate over the curve side. And if you just collect all of them and consider arbitrary possible coproducts of them, and that they give you the entire cohomology. In other words, every cohomology class is tautological. Then the second, once you know the generators, it's natural to ask what are the relations. And unfortunately, this is not known yet. So the only, so for the model of vector bundle, there's a lot of progress by Mumford and Kerwan and others who proved that actually, so they gave a complete description of all the tautological relations for the model of vector bundles, but for the model of Higgs bundles, this is still largely unknown. The only known case is the rank 2 case, which was due to Hausel and Thaddeus more than 20 years ago. So then the next story is, okay, so you don't know all the generators, but also maybe numerically, you don't know all the relations, but numerically probably you can do all the Beatty numbers. Actually, this was known with a lot of hard work by Schiffman, who produced a formula, a very complicated formula for the Beatty numbers of this model of Higgs bundles, and he conjectured, it was conjectured this formula is equivalent to some much simpler formulas, and this identity was further proved by Mallet 3 years after Schiffman's work. Yeah, I will show you the formula explicitly in a few minutes. So Schiffman's original motivation actually partly concerns as a generalization of the Katz polynomial, counting over finite fields absolutely in the composable vector bundles over Riemann surface. And this has connections to Donaldson-Thomas theory and representation theory. Yeah, so now since we know, so Schiffman's and Mallet's work mainly concerns the model of Higgs bundle side, MH side. But since we know that these two modular spaces are the same, I mean, they underline the same topological manifold, so it doesn't matter. We can consider either the cohomology of the left-hand side or the cohomology on the right-hand side. But this is not a trivial bridge. So after you have it, actually you can, so because both sides have different structures, if you use some non-trivial structure on the one side and translate it to the other side, most of the time you get something actually quite surprising. It's not trivial. So let me give you an example of this phenomenon. So the dimension of this modular space is, it's only dependent on R. It does not depend on which degree you consider. And you can ask how this cohomology of the model of Higgs bundle, how this is dependent on the degree, assuming the R, the rank is coprime to D. A priori, there's no easy answer, right? Because if you consider, for example, rank 5 Higgs bundles of degree 1 and degree 3, there's no, or degree 1 or degree 2, there's no obvious connection between these two modular spaces. And in particular, for the modular of vector bundle space, the NRD, you know that they're different. This was known by Hardenau and Seaman, I think more than 40 years ago, who actually realized this by counting points over finite fields as an application of Weil conjectures. But surprisingly, actually for the Higgs modular space, the cohomology, at least the size of the cohomology is independent on the choice of the degree. This is actually, if you concern the Poincare polynomial, this is only a function in R, not in D. And moreover, you know that this entire cohomology ring as a Q algebra is further independent of D. What to convince you that the numerical statement, you can go back to look. If you open Schiffman and Mallet's paper, you can look at the formulas, and after some calculation, probably you can realize that it's independent of D. But here is a direct proof, conceptual proof. So here's the proof. So since the character variety is almost defined over the rationals, the only non-rational part is the choice of and that's the root of unity. So it's defined over this algebraic field. Then for different choices of the degree, the effect, the influence of this choice to the defining equations is only which choice of the primitive R's primitive root of unity. So in particular, how do you think about different character varieties? So they are defined over the same abstract field, but you embed your abstract field differently into the complex numbers, and this will give you different character varieties of different degrees. But this connection is totally missed on the Higgs bundle side. Okay, but now since for fixed R and the two different degrees, they're Galois conjugate, and cohomology as an algebraic invariant. You can use the état cohomology by first you go to the L-additive coefficient and use état cohomology to realize that these two actually are the same. So this is one of the examples that by looking at some structures on the one side of the story may give you something completely non-obvious on the other side. So in other words, the non-abelian Hodge correspondence exchange information in an interesting way.
Is the integral structure different?
Oh, I don't know. I don't have an answer to that. Yeah, here you have to pass to the QL bar, the QL, yes. That's a very good question. And also for, at least to the best of my knowledge, I don't know, for example, if you consider other topological invariants, which are not obviously algebraic, like the homotopy groups, whether they are the same for different choices of D. Yeah, there was a survey paper, I think, by Davesh Maulik a long time ago, which asks whether for different D, actually, they are diffeomorphic. So for Galois conjugate varieties, they can be diffeomorphic or not, but I don't think, to the best of my knowledge, I don't think the answer is no. So, okay, so now, since both sides of the non-abelian Hodge theorem concerns, they are algebraic varieties, so the cohomology actually are endowed with further structures than just a cube algebra. So in particular, so this is the invariant which has showed up many times in this week, which is the weight filtration. So for given any variety, say defined over complex numbers, the cohomology is not only a cohomology, it's not only a Q vector space, a greater Q vector space, but it is actually naturally filtered by the weights. So this is the universal structure for any variety, no matter whether it's compact, no matter whether it's singular. So there's always a weight filtration. And there's many interpretations of different pieces of the weight filtration. So roughly speaking, the weight filtration is governed by, so if you compactify so if your variety is smooth but open, not compact, you can compactify it. And then the complexity of the boundary tells you that the shape of the weight filtration, in the previous talks, this phenomenon has showed up a lot. And there are many tools from tropical geometry and others which can help you to understand certain pieces of the weight filtration for many modular spaces. Yeah, just here's a toy example. If you consider C star, so then if you look at H1, this is one-dimensional. This is the one-dimensional space. So in particular, from the perspective of Hodge theory, this is not of weight one, because it is weight one, then it has to be even dimensional. You should have H10 and H01 part. But there's only one class, so there's no chances of weight one. But the loop, the class given by the loop around the origin for C star actually is a weight two class. It's a class in H1, but of weight two. Okay, so now we have two choices to consider the weight filtration. On the one side, it's the the character variety, and the other side, which is topological, the modular space, the topological side, and the other side is the algebraic one. And so due to the C star action on the Higgs modular space, actually it's relatively simple proof that one can show that the weight filtration on the Higgs modular space side is trivial. So in other words, the Hodge structure is pure. You can study its weight filtration, but it's nothing more than just cohomology. So, however, if, the weight theory for the character variety, this is a very rich subject to study, and it's been studied for decades. And in the next slide, I will tell you actually one of the important open questions concerning the weight theory for the character variety. Okay, so let's just recall to give some feeling about. Actually, this is the original motivation for people like Rodriguez, Villegas, for them to study the weight theory for character variety. So this is manageable due to that a large part of it is governed by counting points over finite fields. So in other words, you can think of the weight theory as some sort of generalization in the character variety case of the counting points over finite fields. So let's recall a theorem by Katz, which is deduced from the Weil conjecture. So assume I give you a smooth variety defined over the integers, which you allow yourself to invert some n. So then, okay, so we can count points over finite fields for this x. So if we know in advance that the counting function is a polynomial function in FQ, you can think of this as, for example, the case if your variety admits a cellular decomposition, this will be the case. Then this counting function over finite field will give you one specialization of this weight function. So if you consider the associate gradient with respect to the weight filtration, so you only remember the weight, which is the I here, but you forget about the cohomological degree. You do the alternating sum for this cohomological degree, neglect all of them. This is nothing but just counting points over finite fields, if you know the counting point is a polynomial function. Okay, so then at least we can access part of the weight information using arithmetic methods. So in particular, counting points over finite fields for the character variety is quite manageable because it essentially concerns the matrices lying in the GOR FQ, satisfies some equations. And this is by the Frobenius formula, this is actually determined by the character table of GOR. So in other words, this is determined, so the function is computable combinatorially. Some examples, if you consider C star 2G, what is this counting point? What is the counting function? It's just Q minus 1, which is the FP points in C star, and you take the power of 2G. Let's consider a more non-trivial example, which is a affine cubic surface, which is actually the character variety for the orbifold P1 in the rank 2 case. What is it? So we know, okay, so projective cubic hypersurface is the model is given by P2 blow up 6 points. So then the counting point there would be 1 plus 7Q plus Q squared, because you have 6 eccentric divisor. And then you remove a triangle, which you remove 3Q. So this is actually the counting function, 1 plus 4Q plus Q squared in this case. So yeah, but in general, Hausel-Rodriguez Villegas HRV gave a closed formula for the weights of the character varieties. So here, let's use the WH to denote the weight polynomial, it's a bi-graded polynomial collecting all the data of its weight information. So here I is the information for the weight. You take the I's associated gradient for the weight filtration, and take the J's cohomology is a bi-graded polynomial, and you collect all the information together. Yeah, well, this is the formula. I don't expect that at the first glance you memorize everything, but so I just want to show you that actually there's a very concrete formula of this weight polynomial for the character variety in terms of combinatorial data, and this is wide open to the best of my knowledge. So but everything's concrete. You can, if you play with this formula a little, you can express. So the left-hand side concerns the collection of all the rank and k. So we already know that the degree does not play a role for the formula. So we just collect the data for all R, rank, and k. And the right-hand side concerns just some combinatorial data concerning the partitions. Yeah, I mean, just at first glance, you can ignore the explicit shape of the formula, but just so the takeaway is that the weight polynomial admits a very concrete but conjectural formula due to Rodriguez-Villegas. So this is a two variable polynomial for Q and T, which remembers the weight and the cohomological degree. But actually, you can do two specializations. One, you specialize the T degree to be -1, which is the point counting formula I mentioned due to Katz's result. This corresponds to point counting on the character variety. But also you can specialize to the Q parameter. And since, this is actually, since the cohomology of the, so this concerns actually topological data, and since the cohomology of the H side, the Higgs side, is pure. So if you specialize with Q equals 1, this actually does point counting on the other side, the Higgs bundle side, which is exactly how Schiffman got started. So, yeah, I mean, the Q remembers the weight, and T remembers the cohomological degree. These are only two things. Okay, so let me close this talk by just mention the P equals W conjecture, which appeared in the title of these lectures, and then tomorrow I will give you a more detailed descriptions of particularly the perverse filtration side, and I will discuss some recent ideas of proving it. So the P equals W conjecture tells you that how to think about this weight polynomial and the weight filtration on the other side, algebraic side, which is the character, which is the model of Higgs bundle side. So since I don't have much, how many? 5 minutes. Okay, so the answer, as you see, the W stands for the weight filtration, and so then the other side is given by not weight filtration, because I mentioned, the Hodge structure for the Higgs modular space is pure. So this is given by something called P, which is the perverse filtration. So this proposed answer was given by Mark Cataldo, Davesh and Luca Migliorini about 17 years ago, so this actually appeared after the HRV form, the conjectural HRV formula. So the proposed answer is that the weight filtration on the character variety side is determined by the topology of the Hitchin vibration. So remember that for the model of Higgs bundle, it has a hyperkähler manifold with a Lagrangian vibration over some base, and attached to a Lagrangian vibration, there is some excess. The Lagrangian vibration itself gives you some extra structure for the cohomology, and this structure is exactly matched with the weight filtration on the character variety side due to this highly transcendental non-abelian Hodge correspondence. In other words, so just an intuitive way of thinking about it is, since I mentioned, so you can think of the character, so the weight filtration to be the measure of the complexity of the boundary of the character variety. So in other words, the P equals W phenomenon, I haven't introduced P, I will do this in a minute, but roughly it says that the complexity of the boundary of the character variety is matched completely with the complexity of the Lagrangian vibration given by the Hitchin vibration. Okay, so but still I have to tell you how to, starting from a vibration, how to turn this into a filtration, which you eventually will match with the weight filtration, which appeared many times in this week. But I think perverse filtration hasn't appeared in this week yet, so but I believe it will appear some of the afternoon sessions in Thursday and Fridays also. Okay, so here is the definition, well, it's the quotation marks definition of the perverse filtration, which actually is stolen from the result of the Cataldo-Migliorini. So, but here the word perverse comes from the the perverse T structure of Valence and Bernstein and Gaber in their study of the perverse sheaves and decomposition theorem. But Mark and Luca managed to provide a complete classical description of the perverse filtration as I wrote here. So you have okay, so this is the fibration you consider whose bases are fine. And then you can take a chain of K-planes. You consider a chain where you consider one dimension, codimension one hyperplane, codimension two, and so on. You manage to make them in generic position. It's a chain of subvector spaces, sub-affine spaces. And then the perverse filtration in this case is nothing but just the filtration given by this chain. So you consider all the cohomology, a total space, and you see where it vanishes after restricting to a certain lambda I, and which index you. So the PKHJ is just the kernel of the restriction of HJ to the HJ of the inverse of lambda, which is dependent on J. So you consider smaller and smaller subaffine space and see what cohomology classes vanish there. This will tell you this is corresponding I step of the perverse filtration. Yeah. So tomorrow probably I will give you a more advanced definition of the perverse filtration, which actually will be helpful in the proof. But now let's take this to be the definition. Thanks to Mark and Luca. Okay, so that's the conjecture. So the conjecture is that non-abelian Hodge theorem match tells you that you can think about the cohomology of the character variety associated with a surface group in two different ways: topological way and algebraic way. And then the highly non-trivial non-abelian, the highly non-trivial mixed Hodge structure. There's only one side you have a non-trivial mixed Hodge structure, which is the topological side. And if you translate it back to the abelian, the algebraic side, it's completely given by the topology of this Lagrangian fibration via the perverse filtration. So in other words, this is what I said. So the topology of the Hitchin map actually sees the arithmetic data of the character variety, namely point counting of M car. So this theorem, this was conjectured by the Cataldo-Hausel-Migliorini 2008, who also proved this for the case of rank 2. And then later, 6 years ago, with the Cataldo and with Mark de Cataldo and Davesh, we proved this for genus 2 and all ranks. And now this conjecture is a theorem. So it's due to, so in 22, this is independently due to the joint, the slide was made by Davesh, so I should, M is Maulik. So this is a theorem by Maulik and myself, and also Hausel, Mallet, Minetz, and Schiffman with complete different methods. I will discuss them tomorrow. And 2 years ago, which is 23, there's also a proof joint with Davesh and Qi Zhengying, who is here. So these three proofs uses completely different structures of these modular spaces by viewing them in different ways, and I will discuss more details tomorrow. Okay, thanks.